this is the flow of the day today that I mentioned just now. The flow of the day that I designed is starting from the map section of the topography, which is a 2D presentation of the map that we're familiar with. Actually, I want to start with familiarization of coordinate system and then go towards map projection and map transformation. But this first section take a lot of time actually during my trial run, so I will skip this in assuming that we have the basic knowledge required to move towards the topography section. But in case you want to know a lot more about this first section, I will share this material after the end of the webinar, and you can see my slide inside the material as well as the presentation notes that I've prepared in the slides. So as I mentioned, we'll go directly into the topography section of the webinar, and we will start with 3D terrain. What is 3D terrain, and then how we can improve this 3D terrain to go into a smart topography section. And then once we have finished with this topography section of the webinar, we will go into the asset monitoring part. We start with a digital asset. What does it mean by digital asset? And then go into the asset monitoring section of the webinar. Okay, so as aforementioned, we will start with a 3D terrain section. So what does it mean by a 3D terrain? A general or conventional practice to develop a terrain is actually starting with a 3D survey. So first, we will determine an area of interest that we want to study and perform a 3D survey over that particular area. Okay, now the technology involved in 3D surveying has evolved according to our historical record. So one of the methods that we use for 3D surveying an area is using a method called LiDAR, which stands for light detection and range method. Okay, this is actually a 3D survey that produce a large collection of points and bundle them together into a point clouds. Okay, point clouds. Inside the point clouds, we have a lot of points as a result of the scanning process, and each point have its own special information. So what does it mean by special information? The special information is a collection of data that we have included into the point as an attribute. So one of the special information that is important to our case is the coordinates, and addition to it is the type of point, such as is it a point over a building or a forest or a tree, etc. And we can also associate some color to these points, so that when we import all of these point clouds into a system that can produce a 3D presentation of the point cloud, we can filter the point by color, or we can show the point clouds by color, showing the terrain special information. Okay, so all this information, 3D survey, point clouds, and special information are bundled together, and then that is how we produce a sample of 3D terrain over our area of interest. Okay, I will show you the exact process later in a video, but this is more towards an introduction to it. Okay, as I mentioned, 3D survey has evolved historically, but don't worry so much. We will not go into depth of each evolution, but just know that the fundamental purpose of 3D survey is to get the point coordinates in reference to a datum. Okay, remember that I mentioned the way that I designed the webinar is actually started from a map representation, which we will cover the coordinates, map projection, and map transformation. In that particular portion, I touch a lot on what reference datum is actually meant here, but you can refer it in the future. When we finish this webinar, as I mentioned, I will share the material. Okay, so as you can see, the evolution of land survey has actually progressed from a very manual approach, whereby the person who is responsible to take the survey go point to point and try to use all the methods and tools available to them to actually pinpoint a point of interest in reference to a given or known data. And then we evolve towards using a GPS and laser scanner, as I mentioned, the LiDAR. We fly over an area of interest, and then the laser will automatically scan the terrain and produce plot of points. Okay. Moving further to that, we use a range of satellite system. Okay, I will mention this in the next slide. What satellite system or method that we're using to quickly get a terrain or elevation model of our area of interest. Okay, so this is the satellite method that I mentioned. Okay, there are many sites actually that offers free and downloadable terrain data. Okay, although the data available to us freely is slightly old or not so current, but they serve the purpose. Our purpose here is to model a 3D terrain, right? So one of those sites that give a free and downloadable source to us is given as example here, which is called as SRTM. What is SRTM? Okay, SRTM stands for Shuttle Radar Topography Mission. Okay, this site is coming from NASA themselves. So what NASA did is NASA launched some satellite to the orbit, and then this satellite will periodically fly over a certain area, such as our area here or our region here, Malaysia. And every time they flew over our region or Malaysia, they will scan the data of our terrain and then store it inside this database, okay, which is called SRTM. Okay, the latest or the most accurate SRTM that is available freely to us is called this one, 30-meter SRTM. Okay, and then you can see the yellow tiles inside this picture. Each tiles represent a dedicated scanning area. Okay, all of these yellow tiles are having similar dimensions. Okay, and then the most important thing is each tile here is using a source CRS. CRS stands for Coordinate Reference System. That is a very important term in case if you want to do some map transformation or map projection later. Okay, the CRS here is using EPSG 4326. Okay, EPSG 4326 is particularly using an angular measurement system, okay, which we know as longitude and latitude values. Okay, by this EPSG 4326, we cannot directly reproduce the 3D terrain in our system, but we need to transform it to a linear measurement system, such as in meters or in feet first, before we can produce a 3D terrain. So we will look at that later. Okay, but the most important thing in this slide is I want to show you that even though we do not have access to a LiDAR or any other 3D survey method, we can actually use open source or free source that is available to us, and the data is quite reliable since it's coming from a NASA mission or Shuttle Radar Topography mission. Okay, moving on, I will show you a sample of the process that we use here in our solution. Our solution is called 3D Experience. In this 3D Experience, we can actually import the cloud of points, as I mentioned, and then produce a 3D representation of it. Okay, I will play the video and I will go through for each process. Okay, as I mentioned, we actually started with a 3D survey, and then that 3D survey produced a cloud of points. Okay, as you can see here, we can actually import a number of formats of cloud of points. The most basic is ASCII or SC. And as you can see, the coordinate system previewed here is not actually in angular dimension or angular measurement, which means the cloud of points given in this file is actually have been transformed and projected into a certain CRS. Okay, that certain CRS is very important to be known, because whenever we want to use external file consisted of multiple points or cloud of points, we need to know which CRS that file is using. Okay, for this example, the CRS that Fai is using is given as RGP. So we need to know what our project is using, the CRS that our project is using, and then based on these two CRS, we can transform each point to its actual physical position in the world. Okay, as you can see, based on the CRS used by the file and the CRS used by the project, okay, the 3D point coordinates are represented in the system. So right now it is not that clear where is the hill shade or where is the mountain range or hill range. So we can change the representation color or rendering color to a hill shade type, whereby by this rendering option we can see clearly which area of the cloud of points is considered as a planar or having some valleys or ridges, etc. And this is the result. So as I mentioned, this result is coming from a 3D survey, right? So by default, example like a LiDAR operation. Okay, for LiDAR operation is coming from a flyover over an area. So we tend to overshoot our area of interest a lot, since we involve we need to understand that the way LiDAR is performed is flyover. So there are some aerial maneuver by the airplane or drone, etc. So we need to further reduce our portion of cloud of points here, specifically focusing on our area of interest only. So in this case, although the cloud of points is very big, it covers a lot of area, but we only concern about this area of interest, which is very small compared to the whole cloud of points. So what we do is we highlight the area of interest and then we extract the cloud of points. We extract the cloud of points for that particular area of interest only, and the rest we can just discard it or hide it for later purpose, for later usage. So actually, this is the general process involved in generating a simple 3D terrain. Okay, so moving on. Previously, we have seen that we can import our 3D survey data, produce 3D points in the system, and now what we can do further is we can actually generate subsurfaces to it. So example here, this cloud of points coming from a 3D survey scan, similar to previous method, but as you can see, we have some missing data or imperfections during the scanning, whereby some particular areas, due to some reason, is not captured perfectly during the scanning. So what we can do here, I will show you here in this video. So any particular area that is missing some points or data, we can stitch it together during the importing process of the 3D cloud points. So as you can see, we can generate the 3D surface, but due to the missing points, we don't have the 3D surface generated over that particular area. So what we can do here is we can expand our coverage in neighboring points so that whenever the neighboring points coincide with the range we specified earlier, it will create for us the 3D surface. And once we have the 3D terrain, okay, this is a simple analysis that we can perform in any terrain that we imported. The most basic and simple analysis that we can perform is producing a contour map or producing the height map of the imported terrain, which is what I'm showing here. Okay, we have the 3D terrain, and then we can produce the contour map of that particular terrain. And we can also specify what is the major line and what is the minor line to be represented in the contour map. Okay, so this is the most basic analysis that we can do. Okay, and then the second one, maybe we can change the terrain color to highlight where is the low portion of the terrain and where is the highest portion of the terrain. Okay, we will go deeper into what is the example of terrain analysis that we can perform. But moving further, okay, we have seen that how we can produce a 3D terrain, and now we will go into smart topography. What actually constitutes a smart topography? If you ask any other person out there, they have their own idea or own concept of smart topography. But in general, a smart topography constitutes three portions of important elements. The first one is the 3D terrain. Okay, any smart topography must have a 3D terrain representation, not only 2D. And then for a smart topography to actually perform its function, it must have some terrain analysis capabilities. Okay, and then what we have the 3D terrain, we have the 3D, we can perform some terrain analysis. What next? Okay, the next one is to perform some modification on the terrain virtually. Okay, what important here is the third, if you ask me what is the most important aspect of smart topography, is actually the terrain modifier, the third element there. Okay, we will go first into what sort of terrain analysis that we can perform. Okay, as I mentioned, the most basic and simple terrain analysis that we can perform is actually these two. Okay, height map and contour map. Okay, this is very straightforward. We have the terrain, we have the elevation, we have the low points and high points. So it's just a matter of reading the data and produce some different visualization to it. Okay, for height map, it's actually a simple method of colorizing a terrain mesh, which consists of applying a color code to each point of the terrain mesh with respect to elevation, as mentioned. And then similarly to contour map is actually a combination of lines that join points of input elevation, as simple as that. Okay, and then show it into our terrain or overlay it into our terrain. So these two are the most simple and most basic, and I believe any GIS software right now, particularly right now in the market, can perform these two analysis pretty well. Okay, so the next analysis that we can perform or we can do onto our terrain is actually identifying which area of the terrain is considered as ridges and valleys. Okay, this is particularly important when we want to perform a further analysis downstream. Okay, for ridges, I'm not sure whether you can see it clearly, but in this first picture, you can see there are two color-coded lines represented on the terrain. So the first one is colored orange, which representing the terrain ridges, okay, the high points of the hill or mountain, and then it create a lines for you. And then valleys are color-coded here as blue color. If you can see it, there are some blue color curves in between the ridges, which represent the low points of the terrain over the hill or over the mountain side. Okay, the next analysis that we can do is identifying the slopes direction of each elevated terrain area. Okay, this slope analysis will identify and show to us the slope vector line. Okay, and it also shows us the direction. Right? We can see that there are some black dots appearing on the terrain, and then for each black dots, they will have its own yellow line representing the direction of the vector or the slope. Okay, combining these two analyses, we can do further terrain analysis. I will show it in the later slide. Okay, so the next analysis that we can perform over our terrain is identifying watershed segmentation. Watershed, what we know as tadahan air hujan. Okay, watershed segmentation. So as previously shown, we have this terrain, right? We have identified the ridges and the valleys, and also we have identified the slopes. Okay, so what this analysis is doing is combining these two information the ridges and valleys combined with the slope, so that it can identify the watershed area of the terrain. Okay, watershed is actually an area of land that drains all the streams and rainfall to a common outlet. Okay, that's why we know as kawasan tadahan air hujan. So each hillside will actually get differentiated or segmented to different areas. Such as in this diagram, I have highlighted two portions of the watershed. One is this white colored watershed here. If you can see from the slide, there is a curve highlighted here. If you can see my cursor, okay, this curve is representing the path taken by a water drop or by any water that's coming from this high point. Okay, this high point here, and that is flowing according to the ridges and valleys analysis that we have performed earlier, and then similarly combining with the slope analysis that we performed, so that this watershed segmentation analysis is generating the shortest path. Okay, the shortest path for a water drop to take from the top point or highest point for this watershed to its lowest point. Okay, the lowest point is called as a basin. Okay, so it also generates the report for you. The shortest path taken for a water drop from the high point to the low point of this watershed is how many meters or how many feet. Similarly, you can produce each report for each watershed segmentation just for reporting purpose. Okay, the next analysis that we can perform similar to watershed actually, but this is more dynamic. What does dynamic means? We can actually pinpoint a certain area of interest or a certain point of interest for that matter by our cursor. So whenever we click our cursor on a terrain, the analysis will run automatically and produce a water drop path. Okay, from the point of click to its basin. Okay, we can have this analysis for multiple point of interest. Okay, what's next is this catchment area. Okay, catchment area combine ridges, valleys, slopes, watershed analysis, and water drop path earlier on, and combining them all together into the single analysis, which is called as catchment area. What does it mean is, example, we have a river flowing in between these hills, right? So that river is represented by this curve, this blue colored curve here. So we want to know which area of the hill or watershed is contributing water to this river, particular river of interest here. So by running this analysis, we can see that for this particular river area, the watershed contributor is given by this green colored result. So as you can see here, this river portion have its water running or coming from these two hillside here. One is over this region and another is coming from this region. So what is the potential usage of this analysis in real case? Example, as a prediction to an event or disaster caused by kepala air or sudden surge of river level due to heavy rain uphill. So by predicting this area where it has high potential of kepala air happening, we can overcome or we can give some warning system to the villagers around that river area. Okay, so that are some examples of terrain analysis that we can perform over our terrain. So next coming is the terrain modifier portion of the smart topography. So for this example, I'm showing two different pictures, but it's actually focusing on the same area. So as you can see here, this first picture is different slightly to the second picture here. What is different? Okay, as you can see, I highlighted this area. So what happens if this particular area experiencing some continuous and severe landslide, obviously the terrain will get will be changed from the original scan environment that we have. So due to the continuous and severe landslide, most probably this terrain feature will transform from this portion over to this portion. Okay, so what happens when this event occur? So we can modify this terrain. Okay, we can modify the terrain data and then rerun all the analysis that we have mentioned previously and study the effect of this sudden terrain uh, deformation. Okay, that is a very simple and straightforward terrain modification that we can use. Okay, the next one is how we can use this smart topography to further improve our roadworks or railworks activities in future. So example here, I'm showing two types of profile. The first one is terrain profile, and the second one is a road profile or road or railwork profile. So this road profile is going across the given terrain profile. So what we want to do is we want to highlight or we want to analyze which portion of the terrain we will need to do some earthworks. By earthworks, I'm referring to excavation works or filling works or any tunneling required. So by a smart topography application, we can actually pinpoint the area of excavation needed to be done, okay, the tunnel excavation areas, because obviously this is some sort of a hill, so it's not very cost effective to excavate the whole hill just for our road to pass through it. So a smart topography application can pinpoint for us which area is appropriate for a simple excavation and which area requires some tunnel because cost effective wise. Okay, and then which area we can do some filling. For example, here this particular area is quite large for filling process. Maybe we can introduce some bridges over this portion of the terrain. Okay, since we are working with a 3D terrain data or 3D data format, we can actually estimate how many volumes are involved in these two particular areas or these two particular activities, which is filling activities or excavation activities. Okay, what is the importance of these two values? Actually, we can estimate our cost roughly earlier in the process, because excavating and filling process involve a lot of labor costs and monetary costs. Okay, this is another example of what smart topography can do for us in terms of streamlining and improving our method of works. Okay, this is focusing on a tunnel area of the smart topography analysis we performed earlier. So by this portion or by this capability, we can actually study the geographical data or bedrock data that we have, because for a more dense data, bedrock involve a lot of drilling. It will incur a lot more cost compared to a less dense bedrock layer. So by this analysis, we can actually see how many volumes for a particular bedrock layer. Okay, and we can do a further cost estimation, further improve cost estimation compared to the rough estimation we did earlier. So by this exercise, we can actually expedite our tunneling system or tunneling work. Okay, so we can do a lot of things in 3D environment as shown here. We can slice the 3D data, not only a 3D surface, this is a 3D solid representation of the terrain. Of course, it all depends on the availability of data. As I mentioned, if we have access to a more complex or accurate method of study, let's say geoelectrical resistivity imaging, just to get the 3D representation of the soil beneath the surface. We can import all of those data into the environment and represent it in a more detailed and accurate modeling, such as this one shown in the video. Okay, so we have gone through what is smart topography, the capability of it, and the potential usage of smart topography. So now, what is asset monitoring? So for asset monitoring, we actually start with asset digitalization. Okay, asset digitalization is a process whereby we consolidate all the assets data coming from various sources, and then we put them into a centralized collection of 3D models. So by this process, we actually transform any physical assets with geospatial information. The geospatial information is still very highly relevant into this process. We need that coordinate system the most in this exercise. So we convert all the physical assets into digital assets with georeference position. Okay, so the assets that we are referring here is actually the street assets or street furnitures. So the idea is we can have as detailed as we want, the 3D assets as detailed as we want, but how can we properly locate them on our terrain is the most important criteria. Okay, without properly locate them on our terrain or 3D smart topography, uh, however detailed the 3D model is not very usable in our course. Okay, so the most important thing during the asset digitalization is the geolocation tag. Okay, there are some sources available to us for digitalizing the asset. Okay, but in general, we can divide it into two areas. Okay, the first one is a government or municipal source. Example here I'm showing is coming from a public accessible source, which is called as data.gov.my. Okay, this is a collection of data for Malaysia region. The data is coming from either government bodies or agencies or municipal agencies. Okay, the second one is more open. Okay, is public and open source. Example here given is OpenStreetMap. Okay, by this public or an open source, we can have a lot of data gathered into the single platform because it's not tabulated. It's actually represented using Google Map. So you can see here there are some points, lines, and areas available to it, and each point, lines, and areas are having their own set of geospatial information, as you can see in the left side panel of the OpenStreetMap. Okay, what do we have? What sort of data that is available in the government or municipal source data or data.gov.my? This is example of it. So every municipal maintains their assets separately, each with their own table format or information. But the most important text that we need to know from this sort of data is the geological information or geospatial information, such as this one. We have this data for lampu isyarat in Ipoh. Okay, the most important thing here is these two columns, the north and east longitudinal and latitude data. Okay, and the rest of it is more towards secondary usage, whereby you have this zone code, the category, location, etc. Okay. But the most important thing to note here is for data.gov.my, the data given here is not really up to date. As example shown here, this lampu isyarat data is coming from Ipoh, and then the data is a reading of data for 2017. So now we are living already in 2021. So this data is already 4 years past us. Okay, this is another example coming from the OpenStreetMap. It is in SML format. So notice that in this example, the timestamp is given here, and the timestamp is actually quite latest compared to the previous example that I've shown. We have the data coming at 2020, 2018, etc. So it is a lot current compared to 2017 data that we have earlier. And one thing to note here is, even though the data is large and quite latest, but how can we really determine that this data is correct? Because if the data is not correct, however latest it is still not usable. Okay, of course we can see that the username here is visible, user ID here is visible, but how can we be sure that this user is an authority and an authoritative person from a particular municipal agency or government bodies? So that's our challenge in getting the workable data for us to populate our smart topography with 3D assets. Okay. Question here is, which EPSG is this SML using? Okay, as you can see here, there are similarly there is a similarities between the data from government municipal source and this open public source, whereby you still have this latitude values and longitude values. Okay, as mentioned earlier, whenever we have these particular values, we know that it is in angular measurement system, so it is using the WGS 84 for world, and EPSG code is 4326. That is a common code used by any GPS system out there. EPSG 4326. So we need to transform EPSG 4326 to whichever EPSG that we're using for Malaysia. Okay, this is what we can do. If we have all the 3D assets properly aligned with geolocation and georeference into our smart topography system. Okay, as we can see, these bridges are located exactly at the physical point of reference in the world. And here, I've taken this example from a China railroad company. So, yeah. Similarly, it started with a 3D terrain, populate all the 3D assets, do some modification if necessary, and then once all the 3D assets are in place, geolocated perfectly, correctly, according to its physical reference, we can see that we can do a lot of things. Example like shown in this video, we can do some simulation, and we can see the details, the level of details of the constructions, such as all the catenaries, all the tracks and track beds, etc. Okay, so back to the main question, our main sources need to be populated early on, need to be correct. So it comes mainly to a single point of interest, which is the question of data readiness. Okay, I consider today is a high time for us to start working together. Authorities alike, agencies alike, work together and populate a single source of data. We can use data.gov.my, or we can use any other collaboration platform that we have. The main purpose is to get all of these authorities or agencies populate their data into that collaboration platform, so that we can have a single source data available at any time for future work in smart asset monitoring or smart city for that matter. Okay, so we will go to assets monitoring now. So assets monitoring consists of digital assets, the relationship between digital assets, physical assets, and monitoring and maintenance activities. So what are the most important tags that we need to know between physical assets and digital assets is the asset ID, the geolocation and status. So for this one, we can use any other any particular any format that we want. We can use IoT, or we can use public complaint to start. As long as we can gather all these three texts into our data source. So now, what is the relationship between digital assets and monitoring and maintenance activities? So for asset ID, for each asset ID is since all asset ID or each asset ID is tied to its geolocation. So by digitalizing the asset, we can automatically highlight or alert the particular monitoring or maintenance parties via automail or mobile or platform to perform their activities. And then lastly, the relationship between monitoring, maintenance, and physical assets is by nature it still requires some physical works. We yet to have any smart physical asset whereby, example, for a street lamp, if the bulb of the street lamp got broken, we still yet to have autonomous bulb replacement system to say. So we still need to have that physical works to be done. So whenever the work, whenever the physical assets are the cycle will be the same. That is what our smart assets monitoring is on. Example questions for asset monitoring. So there are some example questions that are highlighted in this slide. Example here is given by this picture. I have enlarged the problematic any street assets that are having some offline or error status in its tag asset status tag. So which street lights or traffic signals are having problem, or how long has it been down, or how frequent it may function? All of these questions can be answered by having a digitalized assets monitoring system, and the 3D representation is making the monitoring system a lot easier because we can directly see our focus is directly focused towards the problematic area of the assets. Okay, the next example question is what is the effect? Example here, right? This picture, you can see there are some building elevation, there are some high building here, some small building, some low building over there. So what is the general effect of high-rise buildings to sun shadow distribution over an area? Because we don't want to rob off somebody's rights for the sun access, because they do need that sun access. Okay, what sort of shadow analysis? We can run a shadow analysis for a day or a specific time over the whole area. Example given by this video. Okay, this is a sun shadow analysis over a day, whereby you can see the sun is progressing from the east to west and see the shadow progressing according to the sun movement. Okay, this one is a shadow analysis for a single time, but over the whole year. So you can see the sun is moving in this figure 8 motion over the whole area for a specific time. So we can also simulate this analysis towards our 3D assets. You can see the shadow is transforming according to the sun motion. Okay, so this is this sort of analysis can be done since we are using 3D data as opposed to 2D data that we are more familiar with. Okay, these are some other example of questions, such as for this first picture, the question might be how many percentage of each building requiring fire safety checkup. Obviously, this may involve some data collaboration between the civil department and the fire station department, etc. So which area are more susceptible to fire? It depends on the location of the fire station and then the distance of the fire station to that particular area given by the street distance and street congestion. All of that can be answered. And for the second picture here, maybe the question is regarding to what is the population density in an area and which building is having higher population density. So that can be represented in our 3D environment as well. So the main thing is all of the result coming from these dynamic queries can be visualized within the 3D environment itself. And we can present this representation to any particular party of interest. Okay, and another one is we can also perform some asset monitoring dashboarding, whereby example like a central command, we are not concerned with the 3D representation at all. We just need to look at a snapshot of the view of things. So we can do that using our dashboard. So by dashboarding, we can highlight the most important key information that the administration or any parties involved need to know for their reporting purpose. So that can be done as well, since all the assets have been digitalized and all the assets have their own text attached to it. Okay, so that is asset monitoring via smart topography approach. So the conclusion is smart topography is becoming a trend in the near future. We have seen Singapore is developing it. We have seen Brunei is discussing on it. So we might as well embark on the journey and start our own smart topography activity as well. So as I mentioned, 2D representation of a city is no longer suffice to answer additional queries or operational questions we have. Okay, and yeah, the second one is very important, single source data readiness. As I mentioned, this is very important for us to develop a smart city in the future. And combination of a smart topography asset monitoring is the foundation actually for a digital twin city application. So with that, I conclude my webinar and I open the floor for any questions or queries that you have.